Swayam Prabha. Digital India. Educated India.
Hello viewers, welcome back to the lectures on stability of slopes. In our previous lecture classes, we discussed about the infinite slopes, we discussed how to analyze these slopes, and after that we moved on to the finite slopes which are smaller in extent, and there we discussed the method planar failure, where we took the failure surface to be a plane, and then we started discussing about the circular failure cases, where the failure surface is circular, it is a cylindrical surface. In these methods, we discussed that there are two categories. First category is those methods in which we take the whole mass which is above the failure surface, we take it as a whole, as a free body, and then we consider its equilibrium. In the second case, we divide the mass into slices. So, we were discussing the first method, in which we started with the saturated clays. Saturated clays means phi was assumed to be 0 and only C was present, and then we started discussing the C dash phi dash soils. So, here was the method which we were discussing, slopes inhomogeneous C dash phi dash soil. We are considering the soil mass to be homogeneous, and the method which we were discussing was friction circle method. Here is a slope C phi soil, and as usual we have taken a trial circle. This is the arc of the circle, and this is the center, and if we draw a circle here with center O, and if we take the radius r sin phi dash, and we had drawn a circle which we called as friction circle. If you take the point here, and if you plot a line which is inclined at an angle of phi dash, then this line which is at an angle phi dash with the radial vector should touch this circle tangentially. This is what we had discussed last time. The reason is obvious, because this angle is phi dash and here this is the radial vector. So, this distance comes out to be r sin phi dash. So, this line should touch it tangentially. This is what we have discussed. So, this was the friction circle. Then we discussed about the actuating forces. We take up this wedge which is having cylindrical surface here, sliding surface is cylindrical, and weight W is acting in downward direction. The pressure due to water will be acting in radial direction, and we took up the resultant of these two forces, resultant of W and U, let us say that is Q. So, Q is acting in this direction. So, actuating forces, we took Q, we can find out the area of this wedge, and then we can find out the weight, we can also find out its Cg, and we can also find out what is the water pressure acting over here. So, Q is the resultant. Then we discussed about the cohesive forces. So, all along this arc this arc is divided into small segments, and on those segments the small components, the small cohesive forces are C1, C2, C3 and so on. If we plot all these small forces C1, C2, C3, C4 and draw this force polygon, then this line A dash, B dash, this represents the resultant of all these cohesive forces. So, this C A dash B dash, it represents the resultant in magnitude as well as in direction, and this A dash B dash will be equal to AB here. So, length of this chord represents the magnitude of the cohesive forces. Then we found out the line of action. To find out the line of action, what we did was we took moment about point O. So, take moment of all these small forces. So, these forces will be having radial distance r as the lever arm, and when you take the moment about all of them and equate it with the moment of the resultant C, then C into LA should be equal to moment of these forces, and these forces are having their moment arm as capital R, the radius of this trial circle, and by equating the moment, then we got the line of action of force C. And because this chord is always less than arc, this C, this line of action of C will be away from, it will be little bit away from radius r. So, it will be away on this side. So, L, this is L A, this is the lever arm of the force C, cohesive force C. You can find out its line of action. Then, if we take up the resultant of all the intergranular forces, then it is found that this resultant will not be passing through the friction circle which we had drawn, but it will be passing through little bit away. So, this radius of this little bit bigger, I should call it, we can call it modified friction circle. So, this radius will be little bit more than, little bit larger than the radius of the original friction circle. So, and this coefficient k, this radius of this bigger radius is equal to k times the radius of the original circle, and this coefficient k can be obtained from this chart. Here it is the central angle and coefficient k here, and this coefficient k varies from 1 to 1.2 depending on this central angle. So, one can find out this coefficient k and one can draw then the modified circle. Now, when you are able to draw this circle, so the resultant P has to pass tangentially through this, tangentially to this circle. Line of action of this C is known to us, Q was known to us. So, we can draw this polygon, and once this polygon is drawn, you can find out magnitude of P, you can also find out magnitude of C. So, this was the basic concept. Now, after discussing the basic concepts, let us go to the determination of the factor of safety. What we do is we take up a trial circle and then assume a reasonable value of phi m dash. This is the first value which we assume for the mobilized friction angle. Then we calculate the C as the line of action of C, where it acts as we discussed in our previous class. Draw the line of action of C. Also draw the first circle, the trial, the smaller, the second circle, the first circle with radius K r sine of phi m dash. So, here I am talking about this circle. We already drawn this is the failure circle, and here I am talking about these circles. So, this first circle is drawn with assumed phi m dash. So, the radius of this circle is k into r into sine of phi m dash, where k we get from the chart, r is the radius of the trial failure circle. Then plot q, which is resultant of w and u through the CG of the wedge and get point D. So, here this is the line of action of force C, this is the wedge. This wedge will be having this surface as cylindrical surface. Perpendicular to the plane of paper, we have been taking as usual 1 meter. You can find out its CG, you can find out its weight, and then by taking the resultant of W and U, that now we know that Q force, and we draw this Q force through the CG, and we get this point D. Draw tangent to friction circle from point D, which gives direction of P1. So, here it is the intergranular force P1. So, from here now I draw this tangent, the tangent to the first circle, and then it gives you this will be the force P1, and we draw a line parallel to this. So, you can complete this force polygon D, Q and this. So, this is the force polygon which is completed. Get C from the polygon and compute mobilized cohesion. C m1 dash, m1 stands here for the first friction circle, and C is the value of the cohesion which we computed from here. So, this is the C value. C divided by LC, length of chord, gives you the mobilized cohesion, the cohesion which is required to keep this wedge in equilibrium. So, once we get this Cm1 dash, you can find out the factor of safety against cohesion. So, Fc will be equal to the available cohesion, effective cohesion is C dash, and Cm1 dash is the required mobilized cohesion. So, Fc will be equal to C dash upon Cm1 dash. And also factor of safety against angle of shearing resistance against phi, F phi will be equal to tan of phi dash, the phi dash is the available friction angle, divided by tan of phi m dash. Phi m was the first trial which we took to draw the friction circle. So, you will be getting F phi and you will also be getting F c. Similarly, draw other friction circles with different radii and get F c and F phi for all of them. So, here we started with the first one. So, after drawing first one, then the procedure is very simple. This is the second, this is the next circle we have drawn. Again from D we draw a tangent, get this point, complete this polygon, and then get C and so on. So, several circles are drawn around this point O, and for all of them we get F c and F phi. Now, variation of factor of safety may be drawn as shown in this figure. This is the figure we have shown here, it is F phi and F c. So, it is natural that when you take, when F phi is low, you need higher F c, and when F phi is high, you need lower F c to keep the wedge in equilibrium. Draw these points and draw these join these points by a smooth curve like this, and then factor of safety against strength, shear strength, is defined as that factor of safety where F c and F phi both are equal, and it is defined equal to F s. So, the procedure is very simple. Draw a line which is having 1:1 gradient, means 45° angle here, and where it intersects this curve, that gives you the factor of safety, that gives you that particular point where F c is equal to F s. So, the F o s corresponding to line drawn at 45 angle gives F s. This procedure is repeated with other potential failure surfaces and that giving minimum F s is selected. So, here we have done only one trial circle, and for that trial circle we got the factor of safety F s, and this complete procedure is then repeated for other failure surfaces also. Please note here, up to here we were repeating the friction circles. So, we use various friction circles to find out F s. F s is that factor of safety where F c and F phi both are equal and they are equal to F s. So, here the work, the contribution of one trial arc is completed. Then you have to use another potential failure surface, another trial arc, and then you have to calculate next F s. So, you have to then calculate a large number of the, you have to take large number of the trials, and after all those, out of all those trials, out of all those circles, you have to choose that circle which gives you minimum factor of safety. So, that is termed as critical circle, and factor of safety will be corresponding to the slope. Now, this is a tedious procedure, and to avoid these tedious computations, a non-dimensional number connecting the slope angle h, gamma, c dash, phi dash, it has been suggested. We have already discussed this, it is called as stability number. So, this is Taylor's stability number. It is defined as here c dash upon f c gamma into h, and Taylor has published charts for easy analysis. For given beta and phi, the stability number may be obtained and used in the analysis. This is the Taylor's stability number chart. On x axis it is slope angle beta, and on y axis it is the stability number. So, for example, the beta here it is varying 0 to 90°, say beta equal to 40. So, if I take beta equal to 40, then corresponding to these are phi values. So, this is corresponding to phi equal to 5, phi equal to 10, 15, 20 and 25. So, corresponding to phi and this beta, you can read the stability number. For example, if I want to have stability number for beta equal to 40, phi equal to 10. So, this is the point of intersection, and somewhere here this value you can interpolate. If you need the value of the stability number at some intermediate value of phi, for example, let us say you need at 8. So, this curve for 8, the curve should be going in between it, the curve for 8 will lie between the curve at for 5 and 10. You can calculate the values for 5 and 10 and then you can interpolate them. Let us demonstrate the applicability of this chart using this example. Find the critical height of a slope. Here beta is given as 50°, phi dash is given as 20°, c dash is 20 kilonewton per meter square and gamma is 17 kilonewton per meter cube. So, beta is given, phi dash is given, beta is 50, phi dash is 20. Let us see what is the value. So, this is 50, here it is phi equal to 25, this is phi dash equal to 20, So, this value is somewhere here, it is little less than 0.08, you can exactly interpolate it. So, it comes out to be around 0.072. So, NS is 0.072 and it connects C, FC, gamma and H. So, 0.072 is equal to 20 upon FC. This is the, we are calculating the critical height. Critical height means the maximum height which is possible. So, it will be having FC equal to 1. Factor of safety 1 means maximum possible height or the critical height, and gamma here it is 17 and H is HCR. So, by solving this equation you can get HCR. So, it is a very convenient tool, you can do any kind of the parametric analysis also. For example, you can vary gamma, you can vary what if the in the field gamma is going to vary, then you can also find out what happens to the HC, or if C dash is varying, what happens to the H. So, in fact, all these parameters C dash, NS, FC, gamma and H, they are interconnected with each other and you can do any sort of parametric analysis also. So, here we get the answer, the critical height is equal to 16.33 meter. Let us have one more example. It is given for a slope the following data is available. Here the slope angle is 40 degree, gamma is 16 kilonewton per meter cube, C dash is 25 kPa, phi dash is 20 degree, height of slope is given in this case, it is 10 meter, and we have to compute factor of safety with respect to strength. So, with respect to strength means, if you remember just now we discussed Fs. Fs is that value of F where Fc and Fy both are equal. So, let us first assume full friction is mobilized. So, this is our first trial. We assume that the full friction is mobilized. So, for beta equal to 40 degree, phi dash equal to 20 degree. Now, if you refer back to the same chart, from here it is 40 and 20. So, somewhere here you get these values. So, NS comes out to be around 0.051. So, NS is equal to 0.051 and on right hand side you have C dash 25, Fc and gamma into H. So, here phi dash is 20 means it is fully mobilized. So, from here Fc comes out to be 3.125 and we had assumed full mobilization on phi dash. So, Fy is nothing but 10 of phi dash divided by 10 of phi m dash, and here phi m and phi dash they are equal. So, Fy is equal to 1. So, we have got one combination of the values, Fc is 3.125, Fy is equal to 1. What we are looking for is that factor of safety where Fc and Fy both are equal. So, we have to take some trials, and then after taking some trials, then we will be finding out that value of the factor of safety where Fc and Fy both are equal. And you should remember, if Fc is lower, Fy will become high. For example, in this case Fc is 3.125, Fy is 1. So, if it becomes more, this will become smaller to keep the slope stable. So, we are looking for factor of safety with respect to strength. What we are looking is Fc should be equal to Fy. So, now let us take another trial. Now, we assume the mobilized phi m as 15 degree, and again using the same chart, beta equal to 40 degree and phi dash equal to 15 degree, you can interpolate Ns, it comes out to be 0.073. So, again put it in this equation, Ns is equal to C dash upon F c gamma h. So, 0.073 equal to 25 divided by F c into 16 into 10, and now you see F c has reduced, it comes out to be 2.14. And also F I for this case, we had assumed mobilized value of phi m 15. This is the phi dash value. So, F phi is equal to 10 of 20 divided by 10 of 15. So, it comes out to be 2.14. So, we have now taken the trials, different values of phi m dash, ns and f c and f phi. They are given here. We have already shown the calculations for 20 and 15. Similarly, you can calculate the value of these factors of safety for 10 and 5. So, these are the values which are coming, and finally, we will be plotting them against each other. So, here I have kept it f c here, f I here, and we plot these points, join them with a smooth curve, and then we need a point on this curve where f c and f I both are equal. So, draw this line. This is a line which is having 1:1 gradient, means 45 degree angle here, and it intersects the curve somewhere here. Read this value. So, from here, from this graph, we get f c, f I both for this, both will be equal. So, that they will be equal to f s, and this value comes out to be 1.76. So, this is the way we can calculate the factor of safety. Now, charts are also available for contours of equal factors of safety. They are also conveniently, one can use them and get the approximate value of the factor of safety. So, here these charts are available for different slope angles. For example, here this slope angle is 1 vertical is to 0.5 horizontal, and here on the x axis it is phi in degrees, and on y axis it is c dash upon gamma h. So, one has to one can have a relationship between c dash upon gamma h, phi dash, and here these are the different curves for different factors of safety, 2.5 to 1.5, 1.4 and so on. So, for this particular slope angle, these quantities factor of safety c dash, gamma, h and phi dash, they are connected using this chart. So, you can straightway get the values from here. Similarly, this is the chart for slope angle 1 vertical is to 0.75 horizontal, rest of the things are same, phi dash on x axis, c dash upon gamma h on y axis, and you can see this first line is factor of safety equal to 3, this is for factor of safety 2.5. So, you can do the parametric analysis, any one of them may be unknown, maybe factor of safety is unknown, or c dash is unknown, or gamma is unknown, rest of the things are known to you. You can use these charts to compute these, to do this analysis. This is the next chart, it is for 1 vertical is to 1 horizontal, slope angle is 45 degree here, and again factor of safety is 3 for this curve, this is for 3, this is for 2.5, 2 and so on. Here it is the 1 vertical is to 1.5 horizontal, y axis and x axis are the same, and these are the factor of safety values. This chart is for 1 vertical is to 2 horizontal, and this chart is for 1 vertical is to 2.5 horizontal. And finally, this is the chart available for 1 vertical is to 3 horizontal, very flat slope, and this is the factor of safety, this is the curve for factor of safety equal to 3, and again on x axis we have phi dash, on y axis we have c dash upon gamma h. Let us again take an example. This is given, there is a slope and data is as follows. Beta means slope angle is 40 degree, gamma is 16 kilonewton per meter cube, c dash is 25 kPa, phi dash is 20 degree, height of slope is 10 meter. In fact, it is the same problem which we solved some time back, and we have to compute the factor of safety with respect to strength. So, take up these parameters c dash upon gamma h, it comes out to be 0.16. So, on y axis you have to look for 0.16, and the given slope is 40 degree, and when I convert it into this term vertical is to horizontal, it comes out to be 1 vertical and 1.19 horizontal. So, we will have to do interpolation because we do not have directly this curve, but the curves available with us are 1 vertical is to 1 horizontal and 1 vertical is to 1.5 horizontal. So, let us use both of them and then we will interpolate the values. So, phi equal to 20 degree. So, this you take on x axis, and on y axis c dash upon gamma h was 0.16, and use this curve. We have already shown these different charts. Use this chart, you will be getting factor of safety around 1.6. You have to take the intersection of phi equal to 20 and c dash upon gamma h equal to 0.16. So, corresponding to that intersection, then you have to interpolate f s also. So, it comes out around 1.6. Then we use another chart, it is 1 vertical is to 1.5 horizontal, and we do the same analysis for phi dash 20, c dash upon gamma h 0.16, and there I got this value f s is equal to around 2.0. So, now you can very easily interpolate. For 1 vertical is to 1 horizontal, it is 1.6. So, corresponding to 1 horizontal it is 1.6, corresponding to 1.5 horizontal it is 2. You can very easily calculate, interpolate the values corresponding to 1.19, and it comes out to be around 1.75. So, it is the same value which we were getting last time. So, we have discussed the mass methods, and we have not discussed so far about the tension crack which can develop at the upper surface. In case of the cohesive soils, tension crack tends to open up near the top of the slip surface. So, this is a cohesive slope. So, generally a tension crack may develop here, it tends to develop here, and this depth of the tension crack theoretically we can calculate it. And what happens because of this tension crack is that the available shear strength which we get will be only from the remaining length, which is termed here effective length of the trial arc. So, the maximum depth theoretically you can calculate it, it will be 2 Cu upon gamma, and correspondingly when we do the analysis, if this tension crack is likely to develop, then length of the arc should be modified, it should be reduced. And also you can do the analysis that if the crack is filled with water, then additional forces, additional driving moments due to horizontal hydrostatic pressure is considered. There will be additional forces which will be acting. So, if this crack is filled with water, the hydrostatic pressure you can take as a triangular variation diagram. So, pressure diagram will be triangle, and you can find out its center of gravity. You can also calculate how much is the amount of the pressure, total pressure, and then it will create a destabilizing moment. So, that moment has also it should also be taken into account while doing the analysis. So, those were the mass methods, and now I am coming to the next category of the methods, method of slices. These are very common methods and very useful, very prominent, means they are used most of the times, and for the computer programs they are very much suitable. So, here we shall be using the Swedish slip circle method, then we will be discussing about the ordinary method of slices, and then we will discuss the simplified Bishop's method, which is more advanced than these two methods. Let us first start with the Swedish slip circle method. This method was basically developed for saturated clays. So, our assumption in this case is phi is equal to 0 and C is there. So, Cu is more than 0. Here it is a slope, and as usual we have taken a circle, trial circle, center is O, and here this is the failure surface. And let us say the soil mass is not homogeneous here. There are 3 different categories of the soil we have taken at this in this particular case. So, this particular soil in this region is having properties gamma 1, gamma 1 is the unit weight, C1 is its cohesion, and phi, as I told you, it is 0. This is the second layer. Here it is gamma 2 and C2, phi is again 0, and third layer gamma 3, C3, and phi is 0. So, what we do in this case is we divide the mass into different slices. So, here you can see we have divided them. So, this is slice number 1, this is the lines showing the CG of the slice number 1, this is slice number 2, slice number 3, and so on. So, let us say this is nth slice and its weight W is acting here in this direction, in the downward direction, and its distance of its CG from O means moment arm or the lever arm is D. So, when we divide the mass into slices, so we theoretically you can divide in as many number as possible, you can take whatever width you want to take, but to make the calculation simple, what we do is this is the line, vertical line. So, we will be taking one slice ending here, so that because we have to take the moments, so we can straightway take the moment of this slice or this slice. Similarly, where this point, this arc is touching the profile of different soil masses, for example, here, we should take some these slices here also. So, this is the basic concept. Let us say there is a slice, its weight is W, its moment arm is D, D is the distance, the moment will be, driving moment will be W into D, and the resisting moment will be Cu into L, L is the arc length. So, here if I take any slice here, for example, let us say this slice. So, this length into, we have taken 1 unit length perpendicular to the plane of paper. So, Cu into 1 into L, 1 into L is the area. So, Cu into L into 1, that becomes the force. So, Cu into L, this is the force, multiplied by radius, this gives you resisting moment, this is the resisting moment. And arc length you can find out in terms of angle theta. So, here in this case, from here to here there was only one kind of the soil, here to here there was another kind of soil, here to here it was third kind of soil. So, it is convenient if I take this angle, completely this angle, because this particular arc length I can calculate its moment also in terms of this theta. This arc will be equal to r into theta 1 I have to convert into radians. Similarly, here this angle is theta 2 and I can find out the arc length. Here it is theta 3, one can find out the arc length here. So, arc length is pi into theta upon 180. So, here we are taking theta in degrees. So, pi into theta upon 180, this becomes radians, and into r this becomes the arc length. So, resisting moments, when I put it here L, it becomes pi theta upon 180 into r square, where theta is in degrees. Now, it is very simple. The factor of safety will be equal to this resisting moment for all the slices, and I make sum of all of them. So, total resisting moment. So, pi into r square into theta upon 180, because r is constant, pi is also constant. So, this pi r square comes out of this sigma sign, and in this you are left with Cu into theta. So, here it will be pi r square into Cu into theta, and here this is the driving moment, summation of W into d. Let us take an example. Given a slope as shown in this figure, here it is a figure, in this a slope is given. Three different types of the clay soils with phi u is equal to 0 exist at this site. So, there are three soil types, first type, second one and third one. Also, the slope angle is not uniform here. So, this you can see here the beta is something else and here it is something else. Unit weight and Cu values are mentioned in the figure. Determine factor of safety using Swedish slip circle method. So, here these are the values, gamma values 17 kilonewton per meter cube, here it is 18 kilonewton per meter cube, 18.5 kilonewton per meter cube, and Cu is equal to 40, 80 and 100 kPa. So, we divide these this we have taken a trial circle here, center is O and radius of this circle is 45 meter. So, solution is take a trial circle, draw arc of the trial circle and we have measured it, it is 45 meter. Divide the section into number of slices. For making calculations simple, take boundaries at the points where different soil types intersect the arc or where slope profile changes. They should be taken as boundaries. This is what I had discussed, that you should try to keep the boundaries of the slices at this place, and draw a vertical line here at this place. It is immaterial, see their width can change. So, I have kept here these slice number 1 and 2, they are having same width, third is not having the same width. And also second point, one more important point is there, because in this particular example the profile is changing. Here it is the angle is almost 45 and here it is flatter angle. So, we should also keep one slice ending at this particular place. So, with these points the calculations will become simple. Theoretically, you can take any number of the slices, you can take anywhere. So, we have taken here 1, 2 is ending here, third is ending here, then 4th, 5th up to here, then from here the profile changes, slope changes. So, 6th I have taken up to this place, then 7th is, you can see 7th and 8th they are having same width. So, I had this point here. So, 7 was starting from here. So, I had just divided this area into two parts, and finally, this is the 9th slice. So, when you do it, when you draw this diagram, you have to be careful. Initially start with this. So, for example, this is here the slope is changing, profile is changing. Take one slice ending here, same way slice ending here, here and here. And also this d value, when you take it on this side and when you take it this side, here I am taking it positive and here I am taking it negative, because if the weight, if you look at, this is the center about which we are taking moment, and weight of this slice number 2, it is not trying to destabilize this mass, but it is trying to make it stable. So, its sign of d will be opposite to that of this sign. Also draw vertical line through center and take boundary of the slice. Here also that's I have already discussed. Now, we start with the slice number 1. We have to take the different forces. So, weight is equal to A1 gamma 1 A2 into gamma 2. It is implicit in this analysis. In all these cases, perpendicular to the plane of paper, the dimension is 1. So, if I consider this figure here, I want to know the weight of this slice. So, what I do is I take this one A1 and here it is A2. Why I am taking different? The reason is also, here you have the unit weight is 18 and here unit weight is different. So, you have to take A1 gamma 1, A1 into perpendicular distance is 1. So, A1 into 1 into gamma 1, and this for this slice it will be A2 gamma 2 into 1. Similarly, for slice number 2, A2 will be this much area into A1, this is the area A1 into its unit weight plus this area A2 into this unit weight. When we go to slice number 3, so here this smaller area you have to find out. So, this smaller area into 17 plus this area into 18 plus this area into 18.5. That is the way you will be calculating the weights. Also, you can find out the CGs. You can find out the CG of all these figures. I am taking those CGs at the mid of this slice. It is not going to make much difference. So, for slice number 5, for example, you will be taking this area into gamma 1, this area into gamma 2, this area into gamma 3 and so on. And when we find out the resisting forces, so in this area soil number, this soil which is having Cu equal to 100, that is effective, that is working. This part of this component, this segment of the arc, it is having Cu equal to 80 and this segment is having 40. So, we will find out those components. So, A1 is 0 plus 7.5 by 2 into 7.5. Also, I calculate A2 from that figure, 0 plus 3 by 2 into 7.5. Gamma 1 was this, gamma 2 was this, and then I got W equal to 714.84 kilonewton, and it is per meter length. Per meter means perpendicular to the plane of paper. The moment arm D will be equal to minus 16.25. So, note down, I am taking negative here. It is on the left side of the vertical line passing through the center O. So, W into D, this is the moment. So, I do this calculation for all the slices. Slice number 1, it is having negative d value, slice number 2 is having negative, slice number 3 is having negative, then slice number 4 it is having positive. Now, here you can appreciate that why I ensured that slice number 3 was ending at that particular vertical line. So, here d is 3.75 and then it goes on increasing, and then I calculate these moments of different slices. So, minus 11609 and so on, and then we calculate the sum of the moments. In the formula we have to find out Cu into theta also. So, for slice number 1, 2, 3, 4, 5, 6, all these slices were having their arc passing through the soil, which was having Cu equal to 100, and the angle subtended by these were 53. Let me go back. So, here this angle is 53, this angle is 29, this angle is 14. So, as far as the resisting force is concerned, I can straightway find out using this complete segment from here to here. It is not needed that you take individual slices. So, from 1 to 6 directly you can take, and we have already taken care that the slice is ending here. Otherwise, we would have calculated it in little bit another way. We can also calculate it for individual slices. So, we get Cu. So, for slice 1, 2, 3, 4, 5, 6, Cu is 100, theta is 53, Cu into theta comes this much. Similarly, for 7th and 8th slice, it was 80, theta was 29, and last slice number 9, Cu was 40 and theta was 14, Cu into theta was 560. So, you get summation of Cu into theta also. Now, finally, we have to keep these things in the equation. Factor of safety is pi r square summation of Cu into theta upon 180 summation of W into D. So, pi 45 square 180 8180 divided by this value, and we get Fs is equal to 1.46. So, we have completed this procedure for one trial circle. So, this is a note I have put here. This factor of safety is for the trial circle considered in this example. We have to take another trial circles and repeat this entire procedure to get the critical circle, which has the minimum factor of safety. So, after Swedish slip circle method, now let us move on to the next method, which is called as ordinary method of slices. In short, it is written as OMS. It is also called as Felenius method or Swedish method of slices. In previous case, we had phi equal to 0. So, it was a simple case. Now, it is little bit complicated, little bit having more advanced nature of the method. So, for this it is for the phi is greater than 0 and C is also greater than 0. So, it is for C phi soil, and the basic concept is same. We assume a trial failure surface and then divide the mass above the failure surface into vertical slices, and depending on the nature 8 to 10 will be sufficient, though there is no hard and fast rule. Then we have to consider the forces on each of the slice. Like we did in the previous case, here also we will be considering the different forces, which we will discuss later on, and then we have to find out the moments and then factor of safety. And one very important assumption in this method is that the side forces are assumed to be equal on both sides of the slice, and they are not considered in analysis to make the problem determinate. In fact, this is the case So, here let me explain it. This is the slope which is divided into 1, 2, 3, 4, 5 and so on number of slices, and this is the slice here. It will be having some forces on the sides also. So, here also it will be having forces, here also it will be having forces along the vertical direction, and in this direction, in horizontal direction they may have forces. In this analysis, we are considering that these forces are equal to each other. Otherwise, this problem becomes indeterminate problem, and rest of the forces are W, and then the forces which are trying to resist the sliding and the water pressure and all those forces which we have been considering. So, in this method we will neglect, we will ignore the forces on the sides. So, its detail I shall take on the next turn. So, in today's class we have discussed about the friction circle method in detail, how to find out the factor of safety. Then we discussed the stability number, the graphical methods using which one can approximately calculate the factor of safety. Then we have started our discussions about the method of slices, and the first method we took was for a special case where phi is equal to 0, Swedish slip circle method, and now we are continuing with the discussions on the ordinary method of slices, and in next turn we shall continue with this discussion. Thank you.